I guess we can start. Last week I asked for this evaluation group, and there were some people volunteering. I think you sent me a mail, right?
I forgot to send
you were also okay. I'm sorry because I didn't leave my mail address on Wiki, so it wasn't so easy to find me. But now I made a link to a page, so you'll find my mail on this one. I think there was another one too, but he's not here, so yeah. Anyways, just to send to that address, and I will list you here, and we'll get back to you later on when this will be. Are you after lab on Tuesday or lecture on Thursday? Are you free then, or so maybe we'll do? I guess that in 2 or 3 weeks' time we'll have the first evaluation. And I think that I will try to list your mails here. So send me the mail that you want me to use. And then if people have issues, they can communicate that to them. And then they can take that up with me and also Carl. So we can sort of, adjust ourselves if you're dissatisfied with something, for example. Okay, so let's start with the main things. Let me see if this is running. Yeah. Okay, so today we will have cover this topic of the course, the 3D map, basically. And now things are getting a bit more interesting because we can start to move things around. Until now we basically, placed triangle in the coordinate systems and looked at different colors and those sort of things. And so this is all about movement and how things move with respect to each other and so on and so forth. Now, it's a bit mathematically intensive, so this is one of the more heavy lectures. I try to make it as explainable as I can, but I would also encourage you to go through this afterwards. At the end of this talk, there's a lot of references, so go through it and try to get it in your head. It's basically linear algebra in some way or another. Certain things it's very important to understand, other things it's not that important by now because you have code that you basically plug things into and it will work out for you. But I encourage you to just go through it afterwards and get a grip on this thing. Okay, so what is it mainly about? Well, it's basically a mapping from 3D model to a 2D screen. So you have some model here. It's not so easy to see what it is. It's actually a head of a monkey. It's appearing in many of these applications. And you basically make that model in some local coordinate system. Like we have made triangles in a local coordinate system. So we have basically had y, x, and then we have placed a triangle in here by certain nodes. So this is a local coordinate system where you're sort of like making our model. Now, of course, if you just don't want one thing, right? You want this to be in some world where things are interacting, or you put several objects into a more complex object and things like that. And that has to be referenced to a common coordinate frame, which you call the world coordinate system. That's where things go on. So in a sense, you have to map your model into this world coordinate system. And that you do by some transformations. Then lastly, you have to map onto the camera because you're always pointing some direction in space. Like you can see that's pointing a camera towards some object. And that has a third coordinate system. And that's really what you see. That's the part of the world you see. And of course, in the camera, this is projected onto a sensor, or in your eyes, for example, it's projected onto your retina. So we have a projection from 3D to 2D also going on, which is sort of like the last transformation. So model coordinates, world coordinates, camera coordinates, and then at the end the screen coordinates, or the two-dimensional world, basically. So a little bit about modeling. We've already seen use triangles, but what the point is that any object you would like to describe, you usually describe it using these primitives, like points, lines, triangles, and quite most often it's triangles, because you can very easily make meshes with them to describe surfaces and whatever you like. When you transform these objects, you transform the nodes or the vertices, and then you sort of interpolate in between, like you do when you draw these triangles, for example. So, for example, a cube you can compose of 12 triangles, because you have 6 faces, and each face can be described by two triangles, and so on and so forth. So you can make your models with that. And then you can take these models and you can combine it into more complex objects. Can you think about some object that you could compose that is more complex? Take a human being, for example, or a car, which I will show on the next slide. So you make all these objects and you put them together into more complex objects again. And each of these objects are basically modeled by some primitive, like typically triangles. Okay, so here's an example of a car. Now in this specific case, you can think about the world as being, where there's this car lives. And then you have all these different objects here that you have made. Now, some things here are only made once, but let's say these two doors, for example, they are very similar. In particular, these four wheels is basically the same object. So instead of making the object 4 times, you take one object and then you move it around in space and attach it to wherever it is. So for example, with the wheels here, can you see what sort of movements you would like to do to put them in the right place?
Rotation.
Yes? Something else?
Reflection.
Well, not necessarily. For the door here, you would need a reflection, I think. But here you can basically rotate it around, and you have. But yes, reflections are also very useful in this case. Yeah.
So you rotate it on one axis, and then you have to move it on the other axis to get to the.
Exactly. So you do what you call translation. Anything else you might think about doing with them? Let's say this whole car moves a bit closer to the screen.
Scale.
Exactly. So the main ones we will look at today to map from this local coordinate system that defines the object onto the global scene. And this car, of course, could again be put into another global coordinate system, basically.
Sorry, I'm late.
No problem. Yeah. So basically, to do that, we have the 3 main ones. Oops, where did I go? Which you already mentioned, but you also have the reflection, flipping is also. You can also do other things like squashing your objects and deforming them a little bit. But for the sake of this, we will basically mainly talk about these 3 today, which is translation, moving in either X, Y, or Z direction, keeping the same shape and direction on it. Rotation, which is basically changing the orientation of the object. And then the last, scaling, basically, to blow it up or shrink it down. Okay, so how do we go about to do these things? Well, to do this we need some concepts from linear algebra. I don't know what you think about linear algebra, if you, a good feeling or a bad feeling, or... Anyway, linear algebra is very, very useful in this course, and you will sort of see its power through here. Now, we won't go into delve into very abstract details around it, but we will pick out the things we need and try to explain why they work the way they do. So that I will try to do. So we need to talk about vectors, we need to talk about matrices, we need to talk a little bit about projective spaces, just to understand this concept of homogeneous coordinates, which is the coordinates we are working on in OpenGL. And then transformation, translation, rotation, scaling, particularly I'll talk about today, although there are others that are also interesting in more advanced things. Basically, the transformations here are done by matrices, as we will see. All of this can be incorporated by one matrix. Right, so just to repeat very basic stuff. A vector, what is that?
Our direction with us at the speed.
Yes, and the speed is?
It could be the x coordinate and the y coordinate, or the square of x plus square of y.
Yep. So basically a number is actually. So it's basically said in the most general way, it's a direction with a so you have something that has both direction and magnitude in one object. And the direction is of course where it points in space, and its magnitude is basically the length, which you can compute by basically using the Pythagorean theorem. Or if somebody recognizes this, it's basically the inner product with itself. So it should be a square root over here. Yeah, so the square root of the inner product with itself. Right, but you can also represent coordinates or numbers or vertices with vectors by binding them at the origin of your local coordinate system. So then basically you can describe it by the number of on the axis, which basically also represent the vector, and the length of that vector is basically the distance from the origin to that point. Basically. Right. It is of course important to separate between point and vectors, because the vector could lie anywhere in space, but if you represent the point by space, it will be bound at the origin. The point is, if you want to move the point around in space with some transformation, you represent it as a vector while we do that. Okay, so just some more repetition from linear algebra. I already talked about the scalar product. If you have two vectors which you often have, let's say you have two vertices and you want to know how they're related to each other, you can look at this scalar product, because it basically tells you the part of one vector in the direction of the other. So in a sense, it's like, you know, projecting this one onto this one, or, you know, otherwise projecting this one onto that one, and sort of see how much one is in the length of the other. So in a sense, measuring them against each other and also seeing how they are related to dimensions. So if these two vectors are parallel, then the scalar product basically becomes the product of the magnitudes of the two vectors. What happens if they are at right angles?
Zero.
Zero, yes, exactly. So a very useful way of using the inner product is to say whether vectors are standing at right angles or not. Because if they are, you could use them to describe coordinates, for example. So the coordinate system is basically a set of vectors, in a sense. But if you would like to use them to represent coordinates, you would like to divide them by their own length, so you get so-called unit vectors. So if you have a vector x here, then you get the unit vector x by taking the original and then dividing by its length, basically. So now you have two length 1 vectors, and if you multiply them by numbers, you'll get the different numbers in the coordinate system. So you can call them a basis for the coordinate system for these two vectors, one pointing in the x direction, one pointing in the y direction. Right? You have also something called, if the vectors are at right angles, we say they are orthogonal. If they also have length 1, like you use them in the coordinate system, you say they are orthonormal. This is just a language used to sort of attach a simple word to what this is. Cross product. You familiar with that? Yes. So basically it's a third vector that you can get out from two. You cross them together and you get the third one, which will stand at right angles at both of them. And if these two are at right angles from before, then basically you have a basis for a three-dimensional coordinate system. So it's very simple to construct things in this way, and you can compute it like that. It's actually a definition given by determinants, but for here I just, show a simple computation where x2 is the second component of the x vector, y3 is the third component of the y vector, and so on and so forth. This is more or less known to people. Yeah, good. So then it became a little repetition. The matrices, what are they?
Yeah, it's just organization of numbers.
Yeah.
Put them together
In the most basic sense.
Column and by columns and rows.
Yeah.
2D.
Yes, that's more or less exactly what it is. So as I say here, it's a two-dimensional organization of numbers. Or if you look at each column here, you can see them as a collection of column vectors. Or if you see the vectors horizontally, you can see them as a collection of row vectors. So there are many ways of seeing it. For our convenience, I think that this picture of a collection of column vectors is very neat, because in OpenGL you don't actually represent matrices as two-dimensional arrays, but you represent them as one-dimensional arrays with where each slot basically contains a column of a matrix. because that's more computationally efficient. So therefore we're really close to this. But also when it comes to transformations, it has a meaning to look at it as a collection of columns. Because if I take this x equals to b, you've probably seen that in many occasions in linear algebra, where you start off with this and basically you say that, okay, I want to solve this equation, I know what b is, I know what a is, and I want to figure out what x is, right? In our case, you can say that x is a known vector. So what then does a x equals b say? What does it mean? Yeah.
Which vector, after you transform it, equals b.
Exactly. So you transform x
You get it.
to b, yes. So you basically take a vector and you move it around. And you can see that by doing this matrix multiplication, because if you look at the matrix multiplication you show over to the right, you see a pattern there. Look at all the first terms for vector b. What are they?
They're the first row.
First. So you see x1, x1, x1 goes in all the first components, then x2, 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 and so on and so forth. So you basically have column multiplied by the original coordinate. And then it's a weighted sum of them. So each of the components of the B is a weighted sum of the columns. And that weight is basically the all coordinates. So what you basically do is that you transform what you set these columns to be determines what sort of transformation you get, basically. So getting all these operations you want is basically to determine what these columns have to be to get that movement we need. And if we put in the right things there, we will get, translation, rotation, scaling, and so on and so forth. Or not necessarily translation, but scaling and rotation we can get, because scaling and rotation is basically multiplications. But translations are
Sum.
exactly. So you just, if you have a vector here at 0, right, and you want to move it, you don't want to do anything else, you just add a number on the x component, right? So now if you have vector x, and this is vector x tilde, then x tilde is equal to whatever original components you had plus tx0. So now I move this to point tx, right? So that's a bit of a drag, because you would like all these operations to be from matrices. And you can do that, but you have to do something with your coordinate system, and you have to use a slightly different set of coordinates. So we'll get back to that. But first, okay, so we see, you can say that if you have a 2 by 2 matrix, it's basically mapping a vector to another vector, or it's mapping the coordinate system into another coordinate system, basically. And how this map, here you see a rotation, for example. So the vector x is rotated. Now it's rotated with respect to something global, right? But you still have the local coordinates surrounding your object, and this is really the key, because you have to rotate it with respect to the world if you want it to move around there, right? In the 3 by 3 case, it's the same thing. You move points around by using these matrices. But we have a problem with this one. And to cope with that, we have to get a little bit more abstract. You can bear with me on this one, because it's a bit, I won't ask any tricky questions about this on the oral exam, but it's nice to know what the background for all this is. And we use these spaces actually a lot in graphics programming. So, anybody knows what projective spaces are, mathematically speaking? You had it covered in math by any means? You have? Anyone else? So I'll touch a little bit upon it without getting into too many abstract details. Basically, I like to, when we talk about projective spaces, I like to use your eye as a model, because basically that's more or less what it is. Of course, this is a more ideal case than your eye, because your eye cannot see in 180 degrees viewing angle, but let's not care about that. So here is your eye, basically, right? And behind here you have a retina. I'll draw it flat for now. Okay. So what happens in the world? How do you see? Well, you have these rays of light coming through. Right. So whatever is bouncing off whatever object out here comes through your eyes as rays, right? Like this. So it's rays through your focal point or your eyes. And then that's basically projected onto this two-dimensional surface behind you, which gives you a representation of a three-dimensional world. And this is exactly the definition of what is called the projective plane. It's defined as rays through the origin in space. Because of course now I draw it flat. In space, this will come in from all directions. So it's basically exactly more or less how your eye works. Now, what are these rays to your eyes? Yes, they can be light, but purely geometrically. If you put a ray in front of you, what do you see?
Lines. Points.
Points, yes,
Not
exactly.
projected points.
So if you point this right at from all these rays represent points in the plane. So if I sort of intersect here, let's say at W equal to 1, I will get a set of points. And I can do, of course, that to W equal to 2. I get the same set of points, right? I will see these points and these distances in a sense as the same size at any distance. But any Euclidean object you will move here will appear to shrink, right? Because they get smaller and smaller compared to the points you use to measure it. So in a sense, this is a way you measure in a projective plane, just as you use a three-dimensional coordinate system to measure in the Euclidean world. So that's what it means. But how would you go about and describe this with coordinates? That's the big question. Yes, another thing. Yeah, you talked about lines. How do you represent lines in this space?
You know a vector, you know the direction of a vector, and you know a point that the lines goes through.
Yeah.
And the direction of the line. Basically, you need those two things, and you can define a line.
Yes, then you can. But what would that be if you see them with respect to this image of rays here? What would they represent? Because all along this rays, every point is basically the same. They have the same meaning, right?
Yeah. Okay. So if from that perspective, you just see points.
Yes, you see points.
But
So
if you know that they're all going to come to the origin,
yeah.
then you also know the direction.
Yes.
And if you subtract the point that you see to the origin, you can get the directions of those lines.
Yes, that's a good point. But I was thinking, if you see a line in front of you, what would that line represent? Okay, let me take the next step. So how do you represent these lines? Because all points along this line is equivalent. Meaning that if, let's say this is W equal to 1, then of course here I'll have this plane go here. So you have your XY plane, basically located at W equal to 1. So now that plane represents, the plane in mathematics, basically. And then these points gives you points in that plane, right? But I could move the plane here and I get exactly the same thing, only that is scaled by a certain factor. This means that if you look at x, y, the coordinates of your plane, here, then to describe this projective space, you add the 1 to it, because it's basically the plane line here. But in projective geometry, this is basically the same as if I should scale it with any number, wx, wy, w. These are equal. And that's why you see these points as rays, right? Because any point along that is equivalent. And this is actually the same w as you see in OpenGL. It's a way of just describing this sort of projective plane, which is really what you do when you map from your three-dimensional world onto a screen. This is more or less the geometry you're talking about. And there's a lot of weird things happening here. I won't go into details, but for example, parallel lines will meet at infinity. You will see lines that would look parallel here. If you look along these parallel lines, there will be like a railroad track converging to one point, right? But the point is that you have a new set of coordinates, which is now, you can rather write this than this product, you could write this as coordinates, big X, which is basically equal to w times x. You could use big Y, which is equal to this one, and then at last you could say that this is basically just double. So the coordinate representation of a projected space is basically a triple. So to describe the projected plane, you need 3 coordinates. And that's when I get back to the question, how would I see a line in this representation? So if I'm now seeing a line here, now the ray for the origin is basically just seen as a point, right? How would this line appear to me? What would that look like in this model? Well, again, you would have equivalent points there, so it would be a plane intersecting in front of you, right? So rays become points, and lines you see are planes. And the orientation of that plane is nice to know because it gives you orientation of lines in space, which you need when you want to rotate things and do those sort of things. And as I told you before, if I set w equal to 1, you get points in space. You know, nice and simple. That's exactly what you do in this drawing. But if I set w equal to something else, then of course to get my right small x and small y coordinate here, I will have to divide these big coordinates with whatever I scale up with, right? So small x here is equal to the big X divided by w, and the small y here is equal to the big Y. Sorry, not so good at drawing or writing. Like that. So then we can basically say that all of these planes are equivalent. Of course, we would just like to put it equal to 1 because that's a simple thing. But you have another possibility. You can let w be 0. And that's also another option you have in OpenGL. Then what happens to these numbers if w gets 0?
That's undefined.
That's undefined.
Well, or you can call it something abstract and weird that people are very
Theoretically infinity.
Yes. You basically get infinity. So it means that you're moving out to infinity in both directions. And I like to use the analogy, and this is actually one of the characteristics of the projected plane that separates it from just being the Euclidean plane, or R2, is that you have these points at infinity. So what you can say is, if you don't understand this now, it doesn't matter. If you understand it, that's great. But I mean, it's not that crucial for the course. But just get what I'm saying. The projected plane, which is basically the projection of the three-dimensional world onto the screen, is the Euclidean plane. R2 here, plus a line at infinity. It's actually a bit misusing to use a line because it's actually a circle surrounding the whole space. And I like to think about it like this. If you set w equal to 0, or you let w go towards 0, you will see a line in front of you extending both directions in space like. So it extends from minus infinity to plus infinity. And this will hit the point at infinity, which is equivalent to where this w is equal to 0. And that tells you what direction your line has. Because if I would change the line like that, it would hit different points at infinity, different points at infinity, and different points at infinity. And now comes the crucial point about the projected plane versus the Euclidean geometry. Let's say now I have two parallel lines. So line 1 and line 2. Where would this hit the point at infinity? Two different points or 1 point?
They would cross, so
Exactly,
the
yes.
same point.
So that's the point. In Euclidean geometry, parallel lines never cross. In projective geometry, and that's what makes it different from Euclidean geometry, every line crosses, including parallel lines. The only thing is that they crosses at infinity. You may ask yourself, what's the point? Well, the point is that you have the possibility to define direction where something hits infinity. So these lines are parallel, they have the same direction, they hit the same point at infinity. And basically, if you're standing here, those lines would point out on this side, so you wouldn't see it right in a sense. But you could turn your head, transform yourself, and then you would see this thing, lines flying off into infinity. And basically they would lie, and that's why they draw them to lie in this big XY plane down here. So what you need to remember about this, if you find this awfully abstract, is that yeah, another thing. Just as I talk about the projected plane here, R2, I'm going to do exactly the same thing with three-dimensional space. I may add some points at infinity, and this time they define a plane. So now it's almost like a sphere surrounding all of R3, right? And where lines hit that space in any direction is the direction of that line in space. And they're also described by these homogeneous coordinates, only now it's the ones we have seen when we have dealt with OpenGL X, Y, C, W. Right? So now we have 4 coordinates. So just like a projected plane is defined by lines through the origin in space, this projected space is defined by lines through the origin in the 4-dimensional space. Now, that's not something we can imagine, but that's how they're defined, and that's totally well defined. And basically, you can then say that the projected space is basically the Euclidean space R3 plus these things that happens at infinity. And now we basically have a reason for these coordinates, because we deal with projected spaces, and then we have these coordinates here, which are now x, y, c, w. So we use this to describe three-dimensional space for the same reason, instead of just using a triplet. And if you find this very, very heavy, what you need to remember is, if you set w equal to 1, it's the same as intersecting the world with this plane at w equal to 1, and you just get points in the normal plane or the normal space. So then they define points. If you set it equal to 0, as I tried to explain, you get the directional lines in space. So in this coordinate system, you can in a very compact way describe both directions and points. And you get another reward. Now, of course, the drawback is that you have to deal with 4 times 4 transformation matrices instead. But you get a reward for that. Because this last component, which is equal to 1, will give you a possibility to describe another transformation using just one matrix. Anybody who can guess what that is?
Perspective.
Yes, that's true. You can describe perspective. That's also very important.
Translation.
But, yes, exactly. Translation. So now we can bake scaling, rotation, translation into one matrix. And that you do by adding this extra. First you get this extra row, which you just basically put equal to 0. If you want to project the transformation, of course, then these are unequal to 0. We won't talk about that today, just to, it gets a bit too much. But to enable translation, you add this last column. And since that is always multiplied by w equal to 1, then we can enable translation with this. So you have your old, in quotation marks, 3x3 matrix up there, which takes care of the rotations and scalings and all that things. And then you get this additional column that takes care of the translation for you. Now, all these operations can be described by 4x4 matrices, which is very neat because you don't have to single out this from, you use the same sort of object to describe them all. Okay. Now, here are all the possibilities in 2D. Remember now I show 3x3 matrices because now we have these x, y, w triplets. So I show them here because it's easier to realize these things in the plane before I go to this phase. Any questions before I start with this?
F means front. F. So we get like F all over the place.
Yeah, I think it's basically to show what happens with some texture on this surface, because it's basically showing a square with something in it, right? And what you move in this square are basically the points, and then you interpolate in between, right? And this is the same if you had this in OpenGL, you would basically move the vertices around, and then of course everything within there would change position or scale or whatever, right? So you can start with the upper one. It's basically identity. You basically multiply any input vector with a number 1, and you get exactly the same. So you get an object that doesn't change at all. Right? You can ask yourself, what's the point? But it's like having the number 1 in the number system. This is sort of like the number 1 for, in this case, 3x3 matrices. And it does nothing. Now, if you change your columns, and you put x, y all the way to the right, then what you get is a translation. And you could see that on the previous slide why you get the translation, because, oops, this one leads to you taking your original components and adding something to them, which is moving you in this example, x units in the x direction or y units in the y direction. And of course you keep the w the same. You don't want to start to mess with the w, so you just put that one equal to 1 in this case. And then scaling. Then you basically again have a diagonal matrix. You know the meaning of a diagonal matrix?
Where all the values in the diagonal are the same?
Well,
Or there's only values.
they're only diagonal values, yes. So a diagonal matrix has only values unequal to 0 on the diagonal, and all the off-diagonal elements are 0, like you see in the three. The one to the left of top there and right top there is basically both diagonal matrices. And if you want to scale your object, so you want to blow it up in x and y direction, then basically I want to blow it up with the number w in the x direction, which means that I just move from, let's say I started at point 1, right? And now I scale it up to point w with this one. And then if I want to do the same in the y direction, I take the second diagonal component and I put the number there that will make it scale in the y direction. So it's all about how you set your columns in your matrix will make you do different things. Rotation I will talk about more in depth later, just to understand why you actually start to rotate by having these sines and cosines in there. This is a clockwise rotation. I will show anti-clockwise later. You also have reflections, which you talked about. So you can, for example, flip. If you want to flip over the y-axis, you put the -1 here instead of +1, because you take whatever x number you have and you flip it to the opposite. Right. You also have these possibilities of sharing, which is called a affine transformation. You can also, as you mentioned, have a general projected transform, which is basically moving in plane through this race I told you here. Then you can get different depth perceptions. Then this triangle will become a trapezoid and those sort of things. But for now, I'll just stick with the rotation, scaling, and translation to, keep it simple. But I would encourage you to go through this, particularly this figure, and try to understand why it becomes this way. Because if you do that, you can start to understand how matrices operate on vectors. Now this you can find on a Wikipedia page on the matrix transformations. I have given the link at the end of this talk. So I encourage you to do that, because it's very nice to know what the math does for you. And you don't need to know so much more than what this says. I will show you in 3D, that you of course have to do, but to get the idea is nice to start here. So unless you understand this already, I will encourage you to do that. Oh, this froze, that's nice. No, it's there. Oh, great. Okay, so I have a couple of more minutes. Any questions before I move to 3D? Is it graspable or is it very difficult? Or
Well, that picture really helps. So it was
Yeah.
it's really helpful.
So go through this, just because I can stand here talking about it. So it's better to sit down and see the mechanism yourself and look how the columns are changing and how they operate on the space. Yeah.
What is H W? What is the H and W?
The H
The top
and
right corner.
I think that there's any number to.
oh yeah. So that's the magnitude you scale with. So if, let's say I start simple, you have a cube here going from +1, -1, -1, +1, right? And W on the first diagonal component means I move these lines out to W, basically. So I get W here instead of W there. And H means the scaling I get in the y direction, so let's say I have H there and H there. So I blow my figure off like that. Here in this case I go from a square to a triangle, to a rectangle. If I put W equal to H, I just blow up the whole square.
But you scale like this, not like just because from that point it scales like from origin. Now there in that drawing it went like all directions.
Yeah, but because this one is that one was sort of like starting at the origin, right?
Yeah.
So you just scale like that. In this case, you have it on both sides, right? So you scale -1. The only thing you don't scale is 0.
Just repeat.
Oh, like the V is all over.
So when you do like that, you blow it up in the XY direction. If you want to tilt it around, you have to rotate it.
Is it like this?
Which you do like with this one. You have to put something on the off-diagonal components to make it move like that, right? Which I'll get back to that one. Yeah, so just we can take a break in about a few minutes, but I will just talk about identity in 3 dimensions. No surprise there. You just add another column with a 1 on it, and this maps every vector to the same vector, basically. And I've given the code in GLM library here. So it's basically a map4. It's a 4 times 4 matrix, and then you basically figure that out by saying map4 1.0 and you'll get a 4x4 matrix as a default with 1s on the diagonal. So it's very simple to generate them in OpenGL. And you can see here why you get the same thing. So you can also go through these multiplications and then just do them to see that you actually get the same vector. And then you see why, because the first component is just multiplied by 1, the second is multiplied by 1, the third is multiplied by 1, multiply everything with 1, you get the same thing. Then translation. Now you just add the scaling in the C direction as well. So I basically showed here, I can change it with big X, big Y, and of course you also scale it out like a cube in the Z direction, the column to the right. And again in GLM you have a very neat way of doing this. So we first specify that you have a 4x4 matrix here, so you use this command GLM translate. And then here you specify that you have a map4 type, which is basically a 4 times 4 matrix. And then you input the 3 values. So in this case, you scale with 10 in the X direction, 0 in the Y direction, and 0 in the Z. Yeah.
Translation is that making the object bigger or
Oh, sorry. Yeah, you're completely right. I was totally off. It's nice that you said, because translation, of course, is moving in space. Let me just draw it so I correct myself here. Yeah. So let's say this is my original object. I want to translate it X units, then I basically move it from here to here. So this is X, if this is 1, I move it to, no, this is, sorry, again, 1 plus X. Right. So I just add this number and I move it there. And the same thing in the Y direction. I will move it out here, for example, then I will move it up here again, and then you will have the point 1 plus Y here. So yeah, that's what it is, actually. You got that, yeah, sorry, I messed up a little bit there. Okay, yeah, so it's basically moving the object along X, Y, or Z axis in this case. X units in X direction, Y units in Y direction, and Z units in Z direction, basically. And so if you want to move it, for example, in this case, if you want to move something 10 units in the X direction and let it stay at the same point in Y and Z direction, you can use this code to do it for you, basically. This one is connected to that example. So we have a vector 10, 10, 10, 1, and you want to move it 10 units in the X direction, you can just input that in this code and you will get that element. Yeah, I think we can take a break. I think I also need it actually because.
Är det går det rätt?